stress. Okay, there what you have learned, stress basically is that force by area. And if you want to know what the state of stress, basically state of stress is the stress is that state of stress at a point, the stress component acting in a plane which passing through that point. Okay, again, since there can be infinite number of planes which can passes through a point, so we can have an infinite number of stress component, and summation of all the stress component or totality of all the stress component we used to call the stress of state at a point. Again, we have learned that the three mutually perpendicular direction, okay, stress component acting in three mutually perpendicular direction is sufficient to map the stress component acting in any other plane. Okay, so basically what we will deal with that, basically what we will do, we'll try to find the stress component acting in three mutually perpendicular directions. Okay, and what we observe that stress component acting in a three mutually perpendicular directions can be written in a matrix form, because here you can see this is we are writing the stress component acting in three mutually perpendicular direction in a matrix form. Okay, so first row is basically stress component here acting in a x plane, stress component acting in y plane, and with a z plane. Okay, so tau xz, basically it is saying that stress component acting in the x plane in the direction of z. Okay, so here also you can see tau the x plane, this is x plane. Okay, this is x plane is perpendicular to this x axis, x plane is perpendicular to the x axis. Okay, the stress component acting in this plane and in the direction of z, so that is our tau xz. Okay, now here what we have learned that stress component acting in three mutually perpendicular directions can be written in a form. Okay, you can write in a matrix form. But again, this stress matrix we used to say stress is tensor, not a matrix. Okay, because the tensor is one n-dimensional array or matrix. Okay, which satisfies some transformation law. Okay, so any matrix, okay, or any array will satisfy some transformational law, particular transformational law, then we used to say that is our tensor. We will see what are the transformational law that this matrix satisfies. Okay, so what we have learned that we can write that all the 9 components, stress component in a matrix form, and if this matrix satisfies some transformational law, then we can say that is a tensor. Okay, and again, when we talk about the tensor, we should also talk about the rank of the tensor. Okay, so for the stress matrix is to have a rank 2. Rank 2 in the sense number of independent quantity required to identify any component in that tensor. Okay, so here you can see, for example, the tau xz. You see the tau xz. Okay, so what we require? We require what are the number of row. Okay, so here number of row is 1. And what is the column number? J is equal to 3. Okay, so here you just see we need two independent quantity to define any component in that tensor. So here we need two components. So basically it is our rank of the tensor is 2. Okay, so similarly, for example, here you can write that ij, tau ij, that is equal to tau 1, 2. That means for our case tau xy. Okay, so basically I is equal to here 1, I is equal to 1, j is equal to 2. Okay, we need only two information. Okay, and that is sufficient to define any component in that tensor. So we used to have a rank 2. Similarly, for a vector, we need only one information, only I, or if you write it like this, okay, 1, 2, 3, 4. So we need only one information, I3, or I3 will be 2. Okay, so we need only one information. So we have a rank 1. Only scalar quantity is to have a rank 0. It's a scalar. Okay, so here stress tensor. So here stress is a tensor because it is to satisfy some certain transformation law, and rank of the stress tensor is to. Okay, so we'll see what are the transpositional law this tensor is to follow. Okay, so basically when we transform that the stress component, okay, with some reference systems. For example, here we have a XYZ component and we have XY and Z axis, and with respect to this axis we have that all other components sigma X, sigma Y, sigma Z, like that we have all 9 components. Okay, now if we change the reference systems, for example here, and if we define the reference system as X dash, Y dash and Z dash, okay, then our stress component, the magnitude, okay, the component stress component will change with respect to that new coordinate systems. Okay, but the physical nature of the stress will not change. Okay, physical nature will not change. Okay, so how to ensure that? Okay, that will be ensured if this transformation, okay, if this transformation follow some certain rule. Okay, so how that rule it is following? What are the rule it is following? Basically, what it is saying that if the stress component have invariant, 3 invariant, okay, then in that case our physical nature of that stress will not change. Okay, so what are the 3? Basically, the invariant we have. So here 3 invariant we have that L1 is the first invariant or I1 first invariant I1. Okay, that is summation of the diagonal term is constant. Okay, so if we have for whole coordinate system, for our X, Y, Z coordinate system, we have the summation of the diagonal term as sigma X. We can write as a sigma XX. We can write sigma YY, sigma ZZ. Okay. Now, if we have that new stress component depending on the new coordinate system X dash, Y dash, Z dash coordinate system, then our summation of the component will be sigma XX dash plus sigma YY dash, okay, plus sigma ZZ dash. Okay. So if we change our coordinate system, okay, in that case, our physical nature of the stress will not change. Though magnitude will change, but physical nature will be the same, and we will ensure by this transformation rule. Okay, so if you follow this transformation rule, okay, then we need to say that stress is a tensor. Okay, so stress tensor basically is to follow this invariant quantity. Okay, the 3 invariant is that summation of the diagonal is equal to 0, and second invariant is that basically determinant of that submatrix, summation of the determinant of the 3 submatrix is constant. Okay, so this is your I2. Okay, and third invariant is the determinant of the stress tensor is also constant. Okay, so here or we have I1, that should be I1 dash, I2 invariant 2, that should be I2 dash, and I3, that should be I3 dash. Okay, so basically invariant means which do not change with respect to changing the reference system. So here our reference system changed from X, Y, Z according to X dash, Y dash, Z dash component. Okay, similarly, in that sense, our individual component of the change, but physical nature is the same. Okay, so basically, if the stress matrix follow that nature, okay, and that we ensure by this 3 invariant quantity. If this 3 invariant quantity we are able to find and see that the stress tensor is basically following this invariant, okay, then we used to say stress is our tensor quantity. And fortunately, stress basically stress matrix, you can say, used to follow these 3 invariant quantities. So we used to call stress as a tensor. Thank you.